In this video, we're going to talk about the concept of differentials as it applies to functions of two variables. Now, a small little change is instrumental in calculus. Consider the following from Cal 1. You have a curve. You can call that y equals f of x. In the good old days when functions only had one variable. Okay. Now, let's say I want to consider a tiny little change in the direction of x. Oh, well, I call that delta x. So here, this is my x value. And then I have another little tiny change. So I have a little tiny change which gives me another x value. So if I take that x and add a little tiny amount, which we often call delta x, then that gives us another point that's very, very nearby. So here, this is sort of blown up, but it's intended that these are supposed to be very, very close to each other. Okay, so you have a little tiny change in the direction of x. The distance from one point to another is that little extra bit that was added. This is called the incremental, or the increment. A little tiny amount, a little increment. Okay, well, notice that if I plug in those two different x values, I get two different y values. Now, they're very, very close to each other, but they are different x values, so I get two different y values. Okay, so over here, I would have, well, that would be f of x, and this one would be f of that thing, f of x plus delta x. Or you could also say h. That's another common way that it's said in Cal 1. Okay, well, the increment is the little tiny distance between here and here. Basically, if you take x plus delta x and subtract x, you get this one. Right? The x's would subtract away, and you'd be left with delta x. Oh, so if I want to define an increment here, if I want to say, what do I mean by delta y? Well, then it becomes pretty apparent that I need to do the same thing. I need to take the bigger one minus the smaller one. Oh, so delta y equals f of x plus delta x minus f of x. Oh, look, it's the numerator from the derivative, right? Change in y over change in x. That's your del y. Your delta y. Delta y over delta x. A little change in y over a little change in x. This is how we develop the derivative in Cal 1. Well, now we're not dealing with curves. We're dealing with surfaces. You're not dealing with y equals f of x. You're dealing with something like z equals f of x comma y. But still, shouldn't we be able to define some little tiny change in the direction of whatever variable I like? Well, sure. So, you have a surface, something like this. I can pick a point. Now, it's not just an x anymore. It's an x comma y. Okay, so there's my point, x comma y. Okay. Now, here, I took a little step in the direction of my x variable. So I said x plus that little tiny change, x plus delta x. But now notice here, I don't have to go in any particular direction. I could go along the x-axis, or I go along the y-axis, or I can do both. I can kind of go diagonally. Okay, so in this case, I don't just say plus delta x. I'd have to go, I'd have to add a little something to my x and a little something to my y. Okay, so here, this would be a little tiny change from one point to another, and instead of just adding delta x, I would have to add delta x and delta y. So here, the little tiny point that's very, very close by would be something like x plus delta x, comma y plus delta y. Okay? So now, I don't just have an increment along my x variable. Now I have two little increments here, delta x and delta y. Okay, but same idea. I've taken a point and moved somewhere very nearby. Well, now if I plug that in to my function, remember this function right here, this surface would be something like z equals f of x comma y. Well, then if I plug this point in right here, I would get some z value, right? And that's what this is. This would be, this z would be f of x comma y. Okay, but what would happen if I plug this one in? What would that z be? Well, that would be z equals to f of, and instead of plugging x and y in, I would plug in x plus delta x and y plus delta y. Okay, so my increment in the direction of x is just some little tiny amount, a little delta x. And my increment in the direction of y is just some little amount, a little distance in the direction of y, delta x and delta y. But now to define my delta z, I have to subtract the functions with those 2 points inside. So here I would say something like, okay, what's delta z? Well, just like over here, it's going to be the higher one minus the lower one. So something like f of x plus delta x, comma y plus delta y, minus f of x comma y. Little tiny change in x leads to little tiny change in y. Step up to space instead of on the plane. Little tiny change in x and y leads to little tiny change in z, your increment. So that leads us to our definition here. Or rather, the first of our definitions. Let's start off with a function. Let z equal a function of two variables x and y. Delta x and delta y are called the increments of x and y. We're keeping the same name that we had in Cal 1, are the increments of x and y. Delta z, which is equal to exactly what we just wrote here, f of x plus delta x, comma y plus delta y, minus f of x comma y. That's the increment of z. So I guess I should say the definition is increments of x and y and increments of z, just like that. Now, let's define something else related directly to this. Let's say we were at this x comma y. All right, so as long as I know where I'm moving to down here on my domain, I can always plug that in up here. But let's say that was hard to compute. Let's say that's hard to figure out, or maybe we just don't know exactly where things are down here. Okay, well, this is analysis. Can we approximate things? Is there a way of saying, okay, even if I don't know exactly where this is, can I figure out more or less where this is? Well, let's take a look. How would I try to get to this point? Okay, well, I would figure out what 2 points in my domain I have, and then I'd plug them both in. Right, but again, let's say I can't come down here. Let's say I have to deal with things strictly up here on the surface. Okay, well, then if I was here, I would try to figure out how much I need to go this way and this way. I need to figure out how much I need to go in one direction and the other, and try to use that to approximate where this point is up here. So I would want to first figure out, okay, if I'm traveling directly from here to here, then what's my slope? Well, I can't really do that though, because here that's at a diagonal. Oh, but I know my slopes along the x-axis and along the y-axis. Those are the partial derivatives. So right here, let me grab another color. I don't care what anybody heard, I didn't just drop anything. So here, if we have our partial derivative, that will tell us our slope along this direction. the partial with respect to x. And if we had the partial with respect to y, well, then we would have, I guess for my illustration, that would be y, and then this would be x. So I could find my slope of my tangent line along my x-axis and along my y-axis. Okay, great, but, I mean, how far do I go, right? I mean, my slope is telling me I'm going this way, but I don't want to go forever that way. I just want to go enough so that I can get to this point up here, or at least close to this point. Okay, so what I need to do is I need to figure out how far to go along this slope. Okay, well, that's where my incrementals come in. Here, if I can figure out how far I go this way. Oh, well, remember, slope is basically what, rise over run? Okay, well, if I can figure out how far I ran, then that'll tell me how much I rise, yeah? If you have the little change in z is going to be, let's see here. I guess let's just write it in vague terms. Slope equals to your rise over your run, how far up or down you go along the z-axis, versus how far you move over left to right, up and down, left and right or back and forth along the xy plane. Okay, well then your rise, which is what we're trying to figure out, how far up we go. We just multiply this over to the other side. So you can say, rise equals slope times run. Yeah, that's not very precise, is it? Well, let's make it precise. Here, our rise, that's going to be a change in the z direction. And now, I would normally use delta here, but delta's currently being used. So here we're going to use a different notation. In fact, one that you're familiar with from Cal 1. We're going to use a differential notation, dx, dy, or in this case, dz. dz is equal to my slope. Well, which slope? There's one along the x-axis and one along the y-axis. Well, I guess I have to use them both, right? Okay, so let's start with the one along the x-axis. So that would be what? The partial of my function with respect to x times my run. How far did I go that way? Oh, well, how far I went that way is my delta x. Oh, but then don't I have to, that would only tell me how far I go up this way. But then don't I need to figure out how far I go this way also? Together, the two of them are contributing to getting me to this point. Okay, so now let me add. I'll do the same thing, except now it's the slope along the y-axis. So this would be dz dy, that's the slope along the y-axis, times my delta y. So here, how far up I go from here to here, I can approximate it by saying, okay, what's my slope? Okay, now how far do I go along that slope? Oh, this far. Okay, so there's how far up I went. Okay, but now how far up, what's my slope over here? Well, there's my slope. Okay, but how far did I go in this direction? I went that far. Okay, so that's how far up I go for this one. Okay, so here I've gone up by that much, over here I've gone up by that much. So if I add those two together, that looks like it gives me a pretty good approximation of how much I went up total. Okay, so this is well, not just part of it, it's total. I do the whole thing. So this brings us to a definition. Let z equal to f of xy. We have a function of two variables. The differentials of x and y. We're going to define them as being the increments. So dx is going to be identically delta x, and dy is going to be identically delta y. The total differential, that's differential of z, the total differential of z is that thing over there. Now notice here, delta x is our differential dx. Here our delta x is our differential dy. So here we're going to write it as a just using differential and using just differential notation here. So here we're going to write that the total differential dz is equal to the partial of z with respect to x times the differential of x plus the partial of z with respect to y times the differential y. So let's take a look at an example. Let's go and find the total differential of the surface of the function z, f of x comma y, equals e to the power of x times the sine of y. All right. Here, the total differential dz is going to be, we're going to take the partial of z with respect to x. Let me just say z sub x times delta x. Times dx plus the partial of z with respect to y times dy. All right. So here that's going to be, we're going to take the partial with respect to x. Here sine of y is constant with respect to x, so it's just a coefficient. It's coefficient e to the power of x. Okay, so the derivative of a coefficient times e to the x is just itself. So that would be e to the x sine of y dx plus, and then here the partial with respect to y. Okay, well now that's the coefficient. So coefficient times sine of y, the derivative would be the coefficient times the cosine of y. And there is our total differential. Note this does extend to a function of higher dimensions. Here we would find the total differential of, let's say, w is equal to e to the power y cosine of x plus z squared. Okay? So here we would simply need a third component for our total differential. dw is going to equal to the partial of the function with respect to the first variable times the first differential plus the partial of the function with respect to the second variable times the differential of the second variable, so w sub y dy, and then we have a third variable, and we do the same thing. It will be the partial of w with respect to z times dz, which is as follows. Here, take the partial with respect to x. That's coefficient times cosine of x plus coefficient. Okay, well the derivative of this coefficient would be 0, and the derivative the derivative of this constant would be 0. And here the derivative of coefficient cosine of x is negative coefficient sine of x. That's going to be negative e to the x sine of x dx. Plus, we take the derivative with respect to y. That's the coefficient now. So coefficient e to the y has a derivative that is itself. So that'll stay exactly the same. E to the y. Oops, sorry, that was a y before, wasn't it? There we go. E to the y cosine y dy. Here, notice this was also a constant with respect to y, just like it was a constant with respect to x. So in both cases, its derivative is 0. But now, with respect to z, this thing is the constant. So its derivative is 0. And so the derivative of z squared with respect to z, we just use the power rule. take your 2, bring it down, subtract 1 from the power. So that'll be the derivative of w with respect to z times the differential of z. Okay. Now, going back up to this illustration here. In Cal 1, we talked about differentiability, and we talked about approximating the change of a curve with its slope. If something is differentiable, well, then you can find its derivative. Okay, cool. And from that derivative, you can find the slope of the line tangent to it. So now, if I take the differential of y, which in Cal 1 we defined as dy is equal to f prime of x dx, the stuff inside the integral, right? If we take that, we could represent this as saying, okay, well, let's see. The derivative, that's my slope. And here, my little change in x, that's this one here. Okay, so this part right here would be my dy. Right? If that's my delta x, which we're saying is the same as dx, it's the same as the differential for the independent variables, then if I simply take the slope and multiply by the base, I end up getting the height. Okay, well, notice in Cal 1, that was a good approximation, as long as you weren't too far from your point. That was a good approximation for this increment. In other words, delta y and dy were approximately the same. Delta y is approximately equal to dy. So if you had differentiability, these two were approximately equal to each other. We're going to have something similar. We're going to have the ability to approximate your increments using your differentials. Actually, I should say that the other way around. You'll have the ability to, actually that was right the first time. You want to approximate your increments with your differentials, yeah. So we'll be able to approximate our increments with our differentials using the definition for both of those in space rather than on the plane. So this motivates why what we saw in Cal 1 is going to now extend into Cal 3. So this gives us our next definition, and it's the definition of differentiability. What does it mean to be differentiable? Now you might say, well, being differentiable means I can compute the derivative, right? Well, the problem is, which derivative? I have a derivative with respect to x, and I have a derivative with respect to y. And even though we haven't talked about them yet, I have suggested that there are other derivatives in other directions. So which one needs to exist? What if they all exist, but some of them are different? So then is my function differentiable or not? What if they all exist and they're all equal except for one? Is my function differentiable or not? So because of the existence of multiple derivatives, the partials with respect to x, y, and as we'll see in later sections, other directions, being able to find a derivative is no longer a good indicator that a function should be called differentiable because there's too many possibilities. So here we're going to define differentiability with respect to the approximation that we saw a moment ago. So definition. Let's begin with a function z is a function of x and y is equal to f of x, y. And everybody's favorite letter in calculus, epsilon. Let epsilon, and we're going to have more than one epsilon. So we're going to call one of them epsilon 1, and we're going to call the other one epsilon 2. These are just regular real numbers that are positive. Just like in Cal 1, when we see epsilon, they could be anything, but it's usually implied that these are small. Okay? So let z be this function of two variables, and let epsilon and epsilon 2 be probably small, but definitely positive real numbers. Okay? If delta z, your increment of z, can be written as delta z equals the first partial of f with respect to x at a particular point, x naught comma y naught, times the increment of x, or if you want to say dx, they are interchangeable for a function of two variables, plus the partial of the function with respect to y at the point x naught comma y naught delta y, plus this constant epsilon 1 times delta x, plus this other constant epsilon 2 times delta y. If this increment can be written as this expression, where as our increments of x and y approach 0, our epsilon approaches 0, our epsilons approach 0, where delta x comma delta y approaching 0, 0, implies that epsilon 1 and epsilon 2 also would approach 0 and 0. Then we say that z is a function that is differentiable at the point x naught, y naught. Basically, going back to our previous illustration, if this approximation here, or rather the sum of the approximations, if the approximation made by this sum is very, very good at approximating this change from here to here, and in fact, not only is it very good, but it actually becomes perfect, because here these little bits of extra stuff go away as you get even closer. If this approximation is good and is perfect as these points get closer to each other, then we call the function differentiable. And in keeping with the same language that we've seen before, if z is differentiable, at all points in a region R, we say that f is differentiable in R. So now that we have a definition for differentiability, let's take a look at some examples. Discuss the differentiability of the function f of x comma y equals x squared plus y squared. All right. By definition, what we want this to be true. We want delta z to equal to f sub x at x naught comma y naught delta x, plus f sub y at x naught comma y naught delta y, plus epsilon 1 delta x plus epsilon 2 delta y, such that epsilon 1 and epsilon 2 both go to 0, as my two increments go to 0. Delta x and delta y go to 0. Okay, that's what I want. Okay, what do I have? Well, I want delta z to equal to this. What does delta z equal to now? Well, we have a definition. Delta z is the total differential. Okay, so the total differential normally equals to this. Oh, sorry, not the total differential, the increment. The increment equals to this. It equals to f of x plus delta x, comma, y plus delta y, minus f of xy. Okay, so that's what we have, which is nowhere near this, but let's see what we can't come up with. What we have is f of x plus delta x, oops, comma, y plus delta y, minus f of x, comma, y, like that. That's our definition. Okay, well, let's see what this is, and let's see if we can't change this to look more like what we have above. F of x plus delta x. Okay, well, take your function and plug in x plus delta x and y plus delta y. Okay, so that'll be x plus delta x squared plus y plus delta y squared. All right, that's what you get when you plug these in here. But now we're going to subtract away f of xy, which is just the original function. We're going to subtract away x squared plus y squared. Like that. Okay, well, we can expand this. If we square this out, that'll give us x squared plus 2x delta x plus delta x squared plus y squared plus 2y delta y plus delta y squared minus x squared plus y squared. And one thing you note is that these four terms subtract away. Those two go away, and those two go away. Okay, so really we're left with 2x delta x plus, I'm going to write these in a slightly different order. I'm going to put these two together. You'll see why in just a moment. Plus, and then I'll go ahead and put those together. Delta x squared plus delta y squared. Okay. And finally, I'm going to go ahead and take these and write them out, not as a square, but as a product of delta x times delta x and delta y times delta y. I'm writing them as a product instead of a square. Okay, now, why did I do that last part? Well, what do I want? I want to be able to write delta z as f sub x. Okay, well, what is f sub x, by the way? Well, let's see. If that's my function, then f sub x is equal to the derivative of x squared with respect to x is 2x, and the derivative of y squared with respect to x is 0. So I can just leave that off. F sub y, well, that'll give me 2y instead of 2x. Same rationale there. Okay, well, look. I have a 2x and a 2y. Those are my differentials. Oh, sorry, those are my partial derivatives. So right here, this is my f sub x times delta x. Isn't that nice? Just like that. That's the reason I wrote these two next to each other, because, oh, look. That's my f sub y delta y, which is what I want next. Plus f sub y delta y plus. Okay, well now, these two terms are supposed to be something, and again, these two somethings are supposed to be small, right? It's implied that they're small numbers. So here this is supposed to be something times delta x. Well, there you go. That's something times delta x. No one ever said it had to be something different than delta x. Oftentimes it will be, but it doesn't have to be. Plus, and same thing over here, that's going to be a something times delta y. Epsilon 2 delta y. Oh, but it's not an, so we're close. We now have delta z written as f sub x delta x plus f sub y delta y plus epsilon delta x plus epsilon delta y. But it's not enough that we have it written that way. We also have to confirm that epsilon 1 and epsilon 2 approach 0 as delta x and delta y approach 0. Well, here note, epsilon 1 and epsilon 2 are delta x and delta y. So, since delta x and delta y are equal to epsilon 1 and epsilon 2, then if delta x and delta y approach 0, 0, well then obviously since these are the same, they will also do the same. Then epsilon 1 and epsilon 2 will also approach 0. Right? They're identical. They're the same thing. So if one does something, the other one will do the exact same thing. So here this shows that this delta z for the increment for this function can be written as f sub x delta x plus f sub y delta y plus epsilon 1 delta x plus epsilon 2 delta y, such that as delta x delta y approach 0, epsilon 1, epsilon 2 approach 0. And so by definition, hey, we got what we wanted. So by definition, yes, this function is differentiable. And note that it doesn't matter what these points are. It doesn't matter what x1, what x naught or y naught are. They're not relevant. They don't make any change here. And here, this would be the same derivative regardless of what that point was. So here, it's differentiable for all numbers for all points on the plane. So our final statement. Thus, f of x comma y is differentiable for all points on the plane. And there we go. Now at this point, you might naturally ask the question, do we really have to go through all that every time we want to confirm if something's differentiable? The answer is, thankfully, no. We do have a theorem that shows that there are some sufficient conditions for differentiability other than having to check the definition. So here, we have a theorem. Let f be, let f of x comma y be a function of those two variables. If f sub x and f sub y, the first partials of f with respect to x and y, if these exist and are continuous, on a region R, on an open region R, then f is differentiable. On that region R. The proof of this one is actually given in your book. So the proof of this one is omitted from this lecture, largely due to the fact that, well, it's already in your book. So proof omitted due to, oh, I don't know. You guys already having it? How do you say that in a formal sounding way? Let's say due to prior exposure. That sounds right. Eh? That sounds formal enough. It's in your book. So if we look at our previous example here, note that f sub x is 2x and f sub y is 2y. So both of these are polynomial functions. All right. F of xy equals 2x, and f of xy is 2y. Okay, those are both polynomial functions, and since they're polynomial, that means they're continuous. So I have a function whose two partial derivatives are continuous. Well, where are they continuous? Well, again, they're polynomials. Polynomials are continuous for all real numbers. Okay, so then here I have a function whose partials are continuous on the region of the plane, all real numbers. Okay, well in that case, f is differentiable on that same region of real numbers. So here, thus, f of x is differentiable for all points on the plane. So mercifully, as long as you can compute the two partials and you can show that they are continuous, then your original function is differentiable. However, as we've seen in previous sections, sometimes confirming the continuity of a function is maybe not always so simple, but it does at least give us another way of thinking about this. So it seems there's a connection between the continuity of the partials and the differentiability of the original function. There is another, much more familiar relationship between continuity and differentiability, which is summarized in the following theorem. And you're not imagining it, this is the same statement that we had in Cal 1, with some modifications to now include a function of multiple variables. Let f of x comma y be a function of those two variables, be a function if f is differentiable at some point x naught comma y naught, then f is continuous at that same point. So just like in Cal 1, just like with functions of a single variable, differentiability implies continuity. Continuity, on the other hand, does not imply differentiability. So here, this is a one-directional statement. If a function is differentiable, then it's continuous. It's not the other way around. If something is continuous, that does not necessarily mean it's differentiable. Right? You say, well, wait a minute, I thought that's what this theorem said. No. This theorem says if the first partials are continuous, then the original function is differentiable. Right? But here, to say if the original function is continuous, then the original function is differentiable, that is not true. All right? So if we're talking about just the original function, not the partials, differentiable means continuous. Continuous does not necessarily mean differentiable. Right? So let's consider the proof of this. Let's start off with the assumption of differentiability. Let z equal f of x comma y be differentiable at the point x naught comma y naught. Okay, so we're starting off with the assumption of differentiability, and we want to confirm that that implies continuity at that point. Okay, well, because it's differentiable, then that means that by definition, by the definition of continuity, by the definition of differentiability, by definition, delta z is equal to f sub x at x naught comma y naught delta x plus f sub y x naught comma y naught delta y plus epsilon 1 delta x plus epsilon 2 delta y, where epsilon 1 and epsilon 2 approach 0 as delta x and delta y also approach 0. Where where epsilon 1 and epsilon 2 approach 0, as delta x and delta y approach 0. Now, also by definition, so up here, this is by definition of differentiability. But now, just by the definition of what an increment is, the total increment, then delta z is equal to f of x naught plus delta x, comma, y naught plus delta y, minus f of x naught, comma, y naught. Okay? So this is by the definition of the increment of z, and this is by definition of what we mean by differentiable. Okay, well, then if delta z equals this and delta z equals that, well then, by the transitive property, that must equal to this. Here we're going to make a simple substitution of notation. Here I'm going to say, let's go and make the following substitution. Anytime I see x naught plus delta x, I'm just going to call that x. So just this, I'm going to write it in a shorter way. These two will mean the same thing, but I write it in a more condensed form. And let's go ahead and let y equal y naught plus delta y. Then we get that f of, or here's that x naught plus delta x, so that's just x, and that's just y. So that's going to be f of x comma y minus, okay, well here I can leave those as x naught, y naught, equals all the stuff on the other side, which is all of this stuff, equals f sub x at x naught, comma, y naught. Here I notice that I have this and this term both have a common factor of x. So let me put these together. So I'm going to write this as f sub x of x naught comma y naught plus epsilon 1 times our delta x. Notice if you distribute that, that does give you those two terms. Plus, and then I'll do the same thing for these two, which both have a delta y. So I'll write that as f sub y x naught comma y naught plus epsilon 2 of delta y. Okay, so here these two are equal to each other, right? Delta z equals that, and delta z equals the other, so that must equal the other. But now notice here, given our substitution, x equals x naught plus delta x, I could solve for delta x here. So here I could simply take the x naught and move it over to the other side, and that would be delta x equals x minus x naught, and likewise here we would have delta y equals y minus y naught. So here, that delta x and that delta y can be replaced by those two expressions. So that's going to be f of xy minus f of x naught plus y naught is equal to f sub x, the x partial derivative of f at x naught comma y naught, plus epsilon 1 times x minus x naught plus f sub y at x naught comma y naught plus epsilon 2 of y minus y naught, after substituting this for that here and this for that here. Okay, now we're almost done. Let's take the limit as x comma y approaches x naught comma y naught, because that's how we're going to find continuity. Remember, a function is continuous at x naught comma y naught if you take the limit as xy approaches x naught comma y naught, you just get f of x naught comma y naught. Okay? So here let's take the limit of both sides. Let's take the limit as x comma y approaches x naught comma y naught on this side. So that'll be f of x comma y minus f of x naught comma y naught is equal to, so I'm going to take the limit on this side, let me take the limit of this side. This will be the limit as x comma y approaches x naught comma y naught of f sub x at x naught comma y naught plus epsilon 1 times x minus x naught plus f sub y at x naught comma y naught plus epsilon 2 times y minus y naught. But notice what happens. As x approaches x naught and y approaches y naught, hey look, this is going to 0. And this is going to 0. So this will go to 0. So anything times 0 will be 0. And this will go to 0. And again, anything times 0 is equal to 0. So you're going to get 0 plus 0 is equal to 0. So this gives us that the limit as x comma y approaches x naught comma y naught of f of x comma y minus f of x naught comma y naught is equal to 0. But notice this is a constant. Right here, this is just a point that you plugged into a function. That's just a number. Limits don't affect constants. So because the limit's not affected by a constant, we can always just move it over to the other side. So here this gives us the limit as x comma y approaches x naught comma y naught of f of x comma y is equal to f of x naught comma y naught. And so, by definition, f is continuous at x naught comma y naught. Because that's what it means for a function to be continuous at that point. If you take the limit as x comma y approaches that point of the function, well, that's the same as if you just took that and plugged it into the function. So by definition, and again, this is by the definition of continuity, by definition, f is continuous at x naught comma y naught. And that confirms our result. Here, we began by assuming differentiability at a point, and in the end we ended up confirming continuity at a point, which was what our theorem stated. If f is differentiable at a point, then it is continuous at that same point. All right, so to wrap up this section, let's take a look at an example of a function that's not differentiable. This will help us, first of all, see an example that not everything is differentiable, but also it will help to clear up some misconceptions of the following, of the previous theorem. The one that stated that, oh, that's the wrong page. Right, it was this page here. The theorem that says let f be a function if f sub x and f sub y are continuous on an open region R, then f is differentiable. This makes it sound like, oh, I just need to find these. Okay, well, no, I need to find them and be continuous. There's still a misconception about this. So let's consider a function that will, first of all, show us what it looks like for a function not to be differentiable, but also hopefully clear up some misconceptions about that theorem. Consider the function as follows. Let f of x comma y be defined as 5x squared y over x to the third plus 3, so long as x comma y, not plus 3, plus y to the third. There we go. Otherwise, that wouldn't be, that would not cause a problem. 5x squared y over x to the third plus y to the third. And it's defined that way so long as x comma y is not at the origin. If it is at the origin, then f of x comma y is just 0. Okay. All right, first of all, let's show that the partial derivatives of this exist at the origin. In fact, not only do they exist, they're actually pretty easy to come by. So now here you might wonder, well, wait a minute. it's piecewise defined at the origin. So how does that work? Do I use this? Do I use this? Well, the derivative of this is 0. Is that right? Maybe. Let's go, instead of wondering about it, let's just do it by definition. F sub x at 0, 0. Let's find that. Okay, well, that's going to be the limit as delta x approaches 0 of f of delta x, 0 minus f of 0, 0. Okay? Here's our definition of the partial with respect to x. Here, really, I should write 0 plus delta x, but, well, 0 plus delta x is just delta x. So here, I've gone ahead and written my definition using that particular function. And then this gets divided by delta x. Sorry, not using that particular function, using that particular point. All right, so let's see what this is. It's going to be the limit as delta x approaches 0 of, well, let's see, I'm taking my f, I'm going to plug in delta x for my x value, and I'm going to plug in 0 for my y value. Okay, well, here, the point that I'm plugging in is not 0, 0. It's something, 0. Okay, so let me go ahead and use this top one. So that'll be 5. My x is going to be delta x squared. My y is going to be 0. All right, like that. Minus, now f of 0, 0, okay, well, that one is just 0. That's how this function is defined. If the point you're plugging in is the origin, then your result is just 0. Okay? All over delta x. Okay, well, that's just the limit as delta x approaches 0 of, notice that's just 0. Right? 0 over delta x to the third, that's just 0. Minus 0 is just 0. And since that's a constant 0, right, over something that's not 0, it's approaching 0, but it's not 0, well, then this whole thing is equal to 0. And that's our limit. Okay, so there we go. It turns out that the first partial with respect to x at the origin of this function is defined, and it's equal to 0. Okay, let's look for f sub y now. And again, we want that at the origin, 0, 0. Okay, so that's equal to the limit of delta y approaches 0 of f of 0, 0 plus delta y. So here I'll just write delta y minus f of 0, 0 over delta y. Okay, well, let's see what that is. That's going to be the limit as delta y approaches 0. Here I'm plugging in something that's not the origin, so I'm going to use the top definition here. And for my x's, I'll plug in 0, and for my y's, I'll plug in delta y. So that'll be 5 times 0 squared times delta y over 0 cubed plus delta y cubed minus f of 0, 0, okay, that is just the number 0, over delta y, which again is just 0. Right? That numerator is 0 divided by y cubed. Right? 0 plus y cubed is just y cubed. 0 over y cubed is 0, minus another 0 is still 0 over delta y. And as I take my limit as delta y approaches 0, here this is 0 divided by something. That's just the limit of 0, which is 0. So here I have the first partial with respect to x exists, and in fact it's the number 0. The first partial with respect to y at the origin exists, and in fact is equal to 0. So here you might think, oh, then obviously my function is differentiable, because my theorem says, okay, both of these exist and are continuous. Yeah, how much more continuous can you get than a constant? Right? It doesn't matter that they're 0, it's the fact that they're constants. Yeah, how much more continuous can you get? People often ignore this last part of the condition. F and y are continuous. They exist and they're continuous. Yeah, we have that on an open region. Here we didn't confirm anything for an open region. We simply confirmed it at the point 0. Remember, an open region has to be a collection of points where all points are interior points. As such, an individual point, an individual value is not going to be an open region. Here we've only confirmed that the partials exist at this particular point. We need an open region to be able to use this theorem. So here, this does not confirm that the function is differentiable. Now, it doesn't confirm that it's not differentiable. In fact, it kind of does nothing other than find f sub x and f sub y at that point. So here, if we wanted to confirm whether it's differentiable or not, we could go back and do it by definition. However, if we suspect something is not differentiable, remember, something is differentiable automatically implies that it's continuous. So if it's not continuous, then it can't be differentiable. Right? If differentiable means it's continuous, then not being continuous means it could not be differentiable. If it rains today, I will wear a hat. Oh, I didn't wear a hat today. Oh, then it must not have rained. Right? If this is differentiable, then it's continuous. Oh, it's not continuous. Oh, then it wasn't differentiable. So here, I can go ahead and show that this one is not differentiable just by confirming that it's not continuous at the origin. And we've seen that from previous sections. If I suspect something is not continuous, I can simply check a few different paths. So let's go ahead and try that. Let's go ahead and take the limit along the path where x equals to y. So here you're trying to approach the origin, and you're doing it this way. You're coming in from x equals to y, like that. Okay. All right, so if x equals to y, then that means when I'm taking my limit, if I say x comma y approaches 0, 0, I can just replace that x with a y or that y with an x. So here I'm going to take the limit as delta x comma delta x approaches, I guess I can just say x and x, right? Because here I'm not checking differentiability, I'm just checking continuity. So I'm really just checking at the point. So here x comma x equals 0 comma 0. Normally I'd say x comma y, but I'm going with the path where x and y are equal, so I can just call the y x. All right, so I'm going to take the limit as x comma x approaches 0 comma 0 of my function. Now here, my function is not at the origin. It's approaching the origin, but it's not at the origin. Okay, so that means I don't have this one, which means this is the one I'm using. All right, cool. So let's go ahead and take the limit as x comma x approaches 0 comma 0. Notice that since we have x comma x, that means all of these y's are also x's. So that's going to be 5x squared times x over x to the third plus x to the third. I replace that y with an x and that y with an x. All right, well, that's the limit as x approaches 0. Notice there's not two variables, it's just one, so I'll just treat it as a regular limit of one variable of 5x cubed over 2x cubed, which is 5/2. All right, these divide away, and you're left with a constant 5/2. And the limit of a constant is that constant. All right, let me go and take this along a different path. Let's take the limit along the path where, let's say, y equals to a minus x. Okay, so now instead of coming at it this way, where y equals x, we come at it from this side, where y is equal to the opposite of x, like this. Okay, well then that'll give me the limit as x comma negative x approaches 0 comma 0. Right here, this should be x comma y, but since y and negative x are interchangeable, I'll call this negative x. That way I'll only have to deal with one variable. So I can replace my y's negative y. All right, so that'll be 5x squared times negative x over x to the third plus negative x to the third. Okay. Well, negative x to the third, that's still going to be a negative. Negative times a negative times a negative is a negative. Okay, so that's going to give me the limit as x comma negative x approaches 0 comma 0 of, that's going to be negative 5x to the third over 0. Because notice, that's x to the third, and that'll be the negative of x to the third, which is 0. This is undefined, and so its limit cannot exist. Okay, so here I try to find the limit as x comma y approaches the origin, and after checking just two different paths, I find that they definitely do not agree. It depends which direction I'm coming from, I may get a different result. So then that means that my function is not continuous. All right, because if my function is continuous, this limit should be independent of any path that I choose. So that means f is not continuous, right, because these are different. Or you can even say because this one's undefined, but it suffices that these two be different. Then f is not continuous at the origin, and thus f is not differentiable at the origin either. So this shows us two things. One, it shows us that we do have to be careful with the conditions of our theorem. Just because our derivative exists, our derivatives exist, and in this case they were even continuous. Right? What's more continuous than a constant? But because they don't have a continuous derivative over an open interval, then we were not able to confirm differentiability. And in fact, it turns out that well, it's not just that we can't confirm differentiability, it's that it's not even differentiable. So in this case, it turned out to be a non-continuous function, which means it was non-differentiable. Right? The other thing it shows us is another example of continuity, and how the relationship between differentiability and continuity allows us to be able to consider one instead of the other when it is more simple or convenient to consider one over the other. So that is it. We wanted to show just one pathological example, one example where things don't work as expected, to show that, well, we should not take things for granted and, in fact, confirm our conditions before we jump to conclusions. In any event, that is the end of our section. That's the end of our topic. If anybody has any questions, comments, or problems over the topic, please make a note of those and reach out. And I hope everyone has a nice day.